Now we're going to explore how similarity of triangles allows us to look at and solve for missing side lengths. The corresponding side lengths of similar triangles are proportional to each other. So if we look at our diagram of similar triangles, if I take the measure of side AX or XY and I divide it by the length of side AB, well, that ratio is going to be equivalent to YZ divided by BZ or BC, as well as XZ divided by AC. And we see that proportional relationship present there. And so we can use that proportion in order to solve for some missing triangles. The important part that you have to pay really close attention to is making sure that you are appropriately corresponding the correct sides to each other. Now notice, angle A and angle X are congruent. Opposite of angle A is side BC. Opposite of angle X is side YZ. That is how we know that BC and YZ are corresponding sides. And that's same true for angles B and C, as well as Y and Z. So we want to find the length of AC. We again have similar triangles, one inscribed inside the other. And so what we can do is kind of look at these triangles separately. And so our smaller triangle is BCD, and our larger triangle is ACD. And again, if we just kind of look, we know that A and B are congruent, which means that sides CD and CE, that should be an E, are corresponding. We know that D and E are congruent, which means that side AC and BC are corresponding. So we can write that out. So we know that AC corresponds to BC, and we know that CD corresponds to CE. And because angle C is just angle C, we know that BD and AE are also corresponding. BD and AE. So we have our corresponding pairs of sides. So they will always have a proportional relationship with each other. And so let's look at our triangles and see what we know. We know BC is 10, and we know that BD is 14. We know that AE is 21, and we want to solve for AC. So since we're using the sides BC and AC, as well as the sides AE and BD, we can set up a proportional relationship with these. Now there's a few different ways you can represent the proportion, but what's really important is two things. Your numerator and denominators have to be related to each other. In this case, AC and AE are the same triangle. And BC and BD are also the same triangle. If I were to flip this fraction, they wouldn't be the same triangle anymore, and that proportion is not going to work. I could also have AC and AE be one proportion, because again, they are the same triangle. And then my proportion will change with having BC and BD in the other ratio. The other thing is that each fraction has to be related to each other. In this case, they are corresponding sides. And so, as well as AE and BD are corresponding sides. In the second example, my numerator are corresponding sides, AC and BC, and my denominator are corresponding sides, AE and BD. So there's a few different ways that you can write the ratios. As long as you follow that convention, you're not going to make a mistake, or hopefully you won't. And so what we can do is actually take the ratio that we have, and we can just fill in the values for the lengths. AC is the one we're solving for, BC is 10, AE is 21, and BD is 14. So we have a proportional relationship, one in which you can solve for x. 14x equals 210, x equals 15, so the length of the side is 15. So now we're going to do a couple more where we have to think a little bit more carefully about which sides are corresponding. So we have two triangles that share a side, and the length of that side is 6. The length of the side CD is 12. We want to find the length of AD. Well, we got to think about which sides are corresponding to each other. And so we have two right triangles here, and notice how we have a short leg, and on the small triangle, the long leg. But on the large triangle, this is our long leg, and this our short leg, and this is our long leg. 12 is the long leg. And so for our small triangle, we have angle A is opposite the long leg. For our large triangle, angle B is opposite the long leg. So angle A and angle B are congruent, which means that for the small triangle BD, which is 6, corresponds to the large leg of DC. The large leg of the small triangle, get a little bit more space. Small triangle, that's what I want, small triangle and large triangle, and we're looking at large leg as well as the small leg. So looking at this structure will allow us to kind of visualize how our ratio is going to look. So on the small triangle, our large leg is BD. But on our large triangle, that's our small leg. On our large triangle, the large leg is DC. Small triangle, our small leg is AD. And so we've got this proportional relationship here that we can use and go ahead and fill in the values. Well, BD is 6 for both of these. DC is 12. So then we just need to solve for AD. 12 equals x over 6. And it's a pretty straightforward relationship. X is 3. It is half the length of the other leg. Last but not least, we want to find the length of BE. That's this entire length here. Well, we've got part of it. BC is 20. We just need to find this side here. Now, what I want you to notice is we actually have two parallel lines and a transversal, which means that angle B here is alternate interior to angle E. And so, given that information, we know that side AC corresponds with side DC. Then we have our parallel lines. Those lines correspond with each other. That means that BC corresponds with CE. And so since we know that BC corresponds with CE, and we know that AB corresponds with DE, we have our proportional relationship, and we can go ahead and solve. 20 over x equals 25 over 50, and we can cross multiply in order to solve, and x ends up being 40. If x is 40, then we just go ahead and add those together, because BE is going to be the sum of those two sides, giving us a length of 60.